Okay. Anyway, so today we're, continuing on through computational statistics. Today we'll cover numeric methods, specifically root finding algorithms. I'm basing my lecture off of the Spurs textbook, chapter 10. Okay. So Monday's lecture on floating point, all of that was mostly off of the IEEE 754. It was also covered in Spurs chapter 9, although we probably emphasized a few different things between the text and what I decided to talk about. Today I'll try to follow a little bit more closely what the textbook covers, okay? So a root finding algorithm is, a computational method that tries to solve, basically, we're going to solve some function f of x where f of x is equal to 0. So basically, you imagine something like this, and you've got something like this. We just want to find what this location is. What is this? This is where, it's equal to 0. So these are considered roots. And we can really only find one at a time, but that's fine. All we're doing is we've got some function x, f of x, and we want to solve where it is equal to 0. Okay. However, it is important to note, and you've probably learned in algebra how to do stuff like this. This is not an algebraic method. All we are doing is we are using a computer to get floating point approximations of these roots, okay? So these algorithms can only give you a floating point approximation of what the root is. Okay, so if you had some kind of, probably in 7th grade or 8th grade you learned the quadratic formula or quadratic equation. That was a way to get roots of a quadratic polynomial. Okay, that was an algebraic way. It gives you an exact representation. If we were to solve the same quadratic polynomial, we would only get approximations if we were to use a root finding algorithm. All right, and so that's a key distinction here. Okay, and this is we might want to ask, like, why do we even bother? Okay, so let's say an useful application. So it might be useful to just find roots in of themselves. Okay, so finding roots is useful. Okay, but it can also be used to solve equations. Okay, so if you have two equations, let's say f of x, and you want to know where do f of x and g of x equal each other, right? So where do these two functions equal each other? Okay, well, all this is doing is just find the roots of f of x minus g of x equals to 0. Okay, if you find the roots of this, you're going to have solutions for this. Okay, roots of this are solutions. Okay, so a lot of things can be put into the form of finding a root. Okay, and when we do, as far as these root finding methods go, they're almost always iterative methods. Okay. Okay, and that means we just start with some initial guess. Okay, and we use that guess. And then the algorithm will say, okay, take that guess, and I'm going to give you an updated guess. All right, and you use that updated guess, and you repeat the process. Okay, and so all the algorithm does is like all of these algorithms. That's all they do. Okay, take the initial guess, take the guess, and then follow the rules, follow the steps. And you just get an updated guess. And then you just repeat. Now you have an updated guess. And then repeat the process. Okay? Follow the steps, get another updated guess. And you keep going over and over and over again. And what we're hoping is that every time you're getting an updated guess, the amount it changes gets smaller and smaller and smaller until a point where we just say, this has converged. Okay? So, we hope the changes between updated guesses shrinks, and then at a certain point we just say, it's not going to get any better than this, okay? And then we'll say it's converged, okay? I don't know where I can write that. At some point we stop. Now, there's a lot of theory that can go into when will we know when an algorithm will converge, when will it not converge. And this can get very complicated, all right? So I'll show you a few algorithms today. Sometimes they converge, sometimes they don't converge, right? So some of them, like the bisection method, and I'll show you that one is like almost guaranteed to give you a solution, okay? Others of them will not, and you're like, okay, well, why don't I just use the one that's going to guarantee me a solution? Well, there's advantages and disadvantages to each of these things. So the bisection method, it's like guaranteed to work, but it takes a long time to converge, okay? Others, they'll converge faster, but only when it works, okay? And so it's like, and a lot of times, we use these algorithms because the function, the math behind the function is so complicated that it's too troublesome to get an algebraic solution, right? Like if you can get an algebraic solution, like if you got a quadratic thing, there's not really a point to using, well, maybe there is, but if you have a quadratic thing, you just throw it in the quadratic equation and then you get your answer and you'll be happy, right? Like we know from algebra, that's going to give us the right thing. But other times you got these complicated things and you're like, okay, I got to find out where this thing is equal to 0. This is where we use numeric methods, okay? So, but for teaching, it's probably best to use these simple examples that we can draw on things, and so probably the examples that I might show you will not be, may or may not be the best times to use one of these things. Okay, so the first method is called fixed point iteration. Okay, all right, and so what a fixed point is where the function of some value is equal to the value itself, okay? So you plug in some number 6 into the equation. If 6 is a fixed point, when you do all the thing, you get back 6, right? And you're like, oh, that's a coincidence, okay? And basically what this means is that, you've got something that looks like this, and then you have Let me draw this. You've got the line y equals x, right? This is not a good example because, all right, let me let me fix my, yeah. Okay, and basically where the thing crosses y equals x, okay, this is a fixed point. Okay, and then this would be a fixed point. And this right here would also be a fixed point. Okay, and so if we wanted to solve where f of x is equal to 0, what we can do is we can just do f of x plus x is equal to x, right? And we'll call this thing g of x. And so this is g of x is equal to x. And then so basically if we find the fixed points of g of x, they will be solutions of f of x, okay? Or they will be roots of f of x. Does that make sense? So if we can find where this thing, so if I call this thing g of x, if I can find out where g of x is equal to itself x, and g of x is in the form of this, then the solutions, the fixed points of g of x will be the roots of f of x, or basically where f of x is equal to 0. Does that make sense to everybody? Okay. And conversely, it doesn't just have to be you add x to both sides, okay? If f of x equals to 0 can be, you know, solved or rewritten in the form of something else, and we'll just call this g of x equal to x. So if somehow you can just, you know, factor f of x or take out one of these x's and turn it into a function, you know, if you've got an x term and you just move that over to the other side or whatever, then again, solving this will give you solutions to this, okay? So if you can rewrite f of x equal to 0 into the form of something else equal to x, then solving for the fixed points of this will give us the roots of the original f of x, okay? Just want to make sure that's okay with everybody. Okay, and so the fixed point iteration, in a situation where it works, the algorithm is really, really, really simple, okay? So I'm going to go to the next slide here, okay? So the fixed point algorithm is very simple. Okay, so start with some guess x sub n. So you have a guess. So given guess x sub n, your next guess, x sub n plus 1, is just equal to g of x sub n. Okay? So how does this work? Okay, so all this is saying, you know, is like, so again, we've rewritten f of x equal to 0 to g of x is equal to x, right? Either we just added x to both sides, or we rearranged the terms somehow so that f of x equal to 0 is now in the form g of x is equal to x, okay? And then so the algorithm is just say, take this, plug that in, g of x, and then your next guess that you're going to use is x is whatever this is, okay? And you're like, well, how does that even work, right? When I first saw this, I was like, surely that can't be right. But it does work, and so let me just illustrate. Okay, so let's say f of x looks something like this, okay? All right. Okay, and then let's say I'm going to add, we're going to have g of x is equal to f of x plus x, right? So we're just basically adding this to, I'm going to create a line here. Oops. Okay, so this is y equals x. All right, and then so if I just added that, then our thing looks something like a little bit tricky or something. Okay, something like this, right? I'm gonna regret this picture here. Okay, and then so let's say we start off with some guess right here at x of n. Okay, so if I go to x of n, at x of n, this is my g of x of n is right there, okay? And g of x of n is right there, right? So this is the value of g of x sub n, okay? And then so this point right here, this is where, this is the value, because this is the value g of x sub n, right here, and this is going to be my new x sub n plus 1. So this location right here, because this is where y is equal to x, this is where this is the value of g of x sub n at this point, and if I'm going to now plug this in and say this is my new x sub n plus 1. Is that okay? And then so if I use this as my new x sub n plus 1, then this value here is g of x of n plus 1. And I can kind of cut across over to here. And this location right here is now this is the location where x is equal to g of x of n plus 1, and I'm going to call this my x of n plus 2. Does that make sense? And so this, if we keep going and going and going, this will eventually just converge to this point right here. This point right here would be a fixed point of g of x, and that will be a solution right here, and that will be a root. So the fixed point of g of x is a root of this thing. Does that make sense? So this is one algorithm, a very simple one at finding fixed points. And if we can turn the original function that we want to find the roots of into kind of this fixed point form, then we can find our roots very easily that way. Just want to, are there any questions on this? Yes?
Just to clarify, g of x equals f of x plus x?
Yes. Okay. So all we're doing, yeah, g of x is f of x plus x, or it could be in one of many other ways. Okay. Now, again, all we're doing is we're trying to just re-express f of x in such a way that the new form is going to be g of x is equal to x. Okay. So let me just give you an example here. I gotta budget my time here. All right. So example. But there, there's some limitations here. Okay. Here, let me, before I write example, just so some problems or limitations with fixed point. With the fixed point method is that there are often many ways to rewrite f of x equal to 0 into the form g of x equal to x. Okay? There's and some of them will converge and some will not. Okay? And it can be frustrating because someone else rewrites it a different way and then theirs works, but the way you rewrote it didn't work. Okay? So let's, we'll take a look at the an example that the book provides. Okay, so let's say our f of x is log x, natural log of x, minus e to the negative x. Okay, this is what we want to do. Okay, so we want to solve where f of x is equal to 0. So find, we're going to say where log of x minus e to the negative x is equal to 0. And we want to find some g of x so that the right-hand side is x and the left-hand side is g of x. Okay? So one way, all right, and this is in the book. So, one way is add x to both sides. All right, and so here I would just do x plus log of x minus e to the negative x is equal to x. All right, and then we would call this g of x, and we're just going to find fixed points of g of x. Okay, but when we do this, we'll find that this doesn't actually converge. Okay, the problem is this will not converge. Another way is, so we start off with log of x minus e to the negative x is equal to 0. Okay, and this, this is frustrating because you're just like, well, how does this make sense? Okay, so here I'm going to add x to both sides. Same thing that I did before. And then, but I'm going to move this term over to the right. Okay? We're going to just move to the right. move to right-hand side. And so what that does is we're going to just subtract off x. Okay, so I got x is now x minus log x plus e to the negative x. Okay, that's all I did. And then when you do this, so we're going to call this thing g of x. Okay, and then just find the fixed points of g of x. And this will converge. Okay. And it's just like, well, how does that make sense, right? I mean, so there is math behind it, okay? And it depends on, if you can take the derivative at the fixed point and the magnitude of the derivative at the fixed point is less than 1, it will converge. But if it's greater than 1, it won't. And that involves taking the derivative and basically doing math that we probably wanted to avoid in the first place, right? And then, further still, another way that the book works is, I could, I'm just trying to write this into the form of x is equal to something else. So I'm going to have, and then if I raise, x, exponentiate both sides, then I would get x is equal to and then so we would call this g of x, and then this will also converge. So, it seems a little arbitrary, at least when you're just rearranging these things, I don't think any of us are so good at math and derivatives so instantly that we would look at this and go, oh yeah, the fixed points of this will have a derivative less than 1. And this one, if you take the derivative at the fixed point, it's not going to be, it's going to be greater than 1, right? That's how, mathematically it will be shown to converge or not converge, but it's sometimes it's a little bit of trial and error on these things, okay? And okay, there is R code in the textbook, and you can kind of play around with it. It's, if you're reading the textbook, the R code is maybe they have all of these, they put them in loops and stuff. You can just try it out yourself very simply and just say, okay, here's my thing x of n, or my initial guess of x of n, plug it into here, and then just whatever that outputs, just plug it back in itself, okay? And then just keep iterating, and then if you try it for something like this, you'll see that eventually it converges to a certain point, okay? And that will be the fixed point of the thing that we're looking at. Okay, so that is fixed point iteration, and I hope that makes sense. I think we'll put something in the homework to try it out, and then you will see if you truly understand or not, I guess. All right. There's other methods. There's Newton-Raphson, okay? And I imagine you learned Newton's method somewhere in calculus, maybe? Okay. So Newton's method that worked in calculus still works, and we can implement it on the computer, okay? What Newton's method requires, though, okay, the drawback here is that it requires that we know the derivative, the form of the derivative, okay? So which is not always possible, okay? So you might have some function in your thing that, you know, ends up being complicated. You know, a lot of times we have these nice little algebraic forms of functions and things like that, but, you know, in the process of your thing, you might have built up a function and you're not even sure how to express your function in math forms, and you're like, well, I don't know how to take the derivative of this. So that would be a problem in trying to use the Newton's method, okay? And the way Newton's method works is basically, you know, some initial guess x of n, okay? And then you find f of x of n and find the derivative, or find the line tangent to f at x of n, okay? And then find where the tangent line crosses the y-axis, no, x-axis, where y equals to 0, okay? So find where the tangent line crosses y equal to 0, okay? Or f of, you know. And then, you know, where it crosses that location, it will be x of n plus 1. So, you know, here you've got I gotta make a better. Okay, so let's say I'm really bad at drawing curves on this thing. Sorry, let me. Okay, so pretend this is smooth. Okay, so let's say this is our initial guess here, okay? So this will be our x sub n. Okay, and then we find the tangent line at this point. So this is, you know, f of x, this point is f of x sub n right here. And we find the tangent line, and I don't know what that looks like. Okay, that's supposed to be tangent, all right? So we find that tangent line, and then we go, oh, okay, where does this thing cross the x-axis? Okay, it's going to cross right here. Okay, so this is our tangent line. So it crosses here, and then we go, oh, okay, well, this is going to be my new guess, x of n plus 1. And then we go, okay, I'm going to go up again to this point. This is going to be f of x of n plus 1. And then we find the tangent line right here. I guess I'll use another color. And, you know, something like this. And then we just continue the iteration. And at some point, you know, it will get closer and closer and closer to the root right here. Okay, so this is going to be x of n plus 2, and so on and so forth until you get to the root. Okay, so where does this thing cross the line? Okay, so basically the tangent line has a slope equal to the derivative f prime at point x sub n, okay? And, okay, so, you know, what is, I don't know, you can say, okay, well, we can find the equation of this thing, right? And this is going to be the point slope form. You got y minus f of x of n is equal to x minus f prime of x of n wait, no, wait, the slope times, what am I doing? What? My brain stopped working for a second here, and now I'm super embarrassed. Okay. Well, gosh, what's going on? Okay. Basically, so because we know the slope and we know where we are here, this point x of n plus 1 turns out to be your current location, x of n, minus the ratio between the height of this point and its slope. Okay, so it becomes f of x sub n divided by the slope of f of x sub n. Okay, and so our next point just ends up being this, and then so this is our algorithm here. Okay, you take your current guess, you got to find the value of the function at your current guess, and you also need the derivative. But if you have those three things, you update your current guess to this, and then you just keep going and going and going and going. Okay, so this is basically the algorithm is this. Okay, this is your algorithm. Okay, update the next guess, x of n plus 1 to be, I'm rewriting this. Okay, and that's just from Newton's method. Okay, and shoot. Okay, so that's Newton's method. If there's something called secant method, which is similar to Newton's method, and if you think of what a derivative is basically you're like taking 2 points separated by delta, and you're just taking the limit until the difference, the deltas reach 0, right? So secant method is basically the same as this, except you have a non-zero delta. Okay, and so it doesn't actually require you to find the derivative. It just requires you to calculate two values of x. You take a value x of n and then an x of n plus delta. So secant method, and I'm going to just do this very quickly. You've got some curve like this. You take a x of n, and then you just have some arbitrary x of n plus a plus a delta, or what does the book call it? No, they call this x of n minus 1, but basically the previous point, all right? And then you join these things. And so rather than the derivative of this, you're taking the line that connects these things. This is called the secant line, right? So it's very similar, but this is the secant line, okay, rather than the not the tangent line. And then and once you get to this point, so it's actually not x of n plus delta. This is going to be your new x of n. New x of n plus 1. So this is the new point right here, and then you're going to just use the last point you calculated. No, shoot, I need straight line mode. So this runs through these points here. Okay, this is now the new secant line. Okay. So what this requires is 2 initial guesses, okay? And this will be x of n plus 2, okay? So this will, you need 2 initial guesses. Okay. And the book calls this one called, we'll just call it x sub n minus 1. And you just keep connecting the secant lines this way, and eventually it will converge to a root here. All right, and so the algorithm here is that your next guess, x sub n plus 1, and you can kind of show that this also works algebraically, is you know, how far over do we go? We take f of x sub n, and then we're multiplying it basically by the slope of the secant line, and that ends up being x sub n, the difference between the two x's over the rise, so the inverse of the slope, I guess. And that's the secant method. I know I'm going through these relatively quickly, but really it's just, they're all iterative methods. You just say, taking some initial thing, you plug it into this, and you're going to get your next guess. And then all you do is you just take that new next guess and you just plug it into the same thing again to get another next guess. Okay? And just geometrically, this is how it works. Okay? And then the last method is called the bisection method. Okay, this is also known as a bracketing method. And this one really requires not a whole lot of thinking. Okay, what it requires, okay, is that you have two endpoints, and you know that the function crosses x somewhere between those endpoints. Okay, and the function crosses f of x. Crosses y equals 0. So let's say this. You got something like this, okay? And all you need is you just say, okay, this is going to be, we're going to call this x on the right and x on the left, okay? And all you need, the requirements is that, so f of x on the right and f of x on the left need to have different signs. So basically you can just say f of x on the right times f of x on the left must be less than 0. Okay? And that's one way to make sure that they have different signs. And then all you're going to do is you're going to just take the halfway point, okay? And you get f, x of m is halfway between the 2 points, okay? And then you calculate f of x of m, okay? Really, and if you don't want to calculate what this is, you really only need to calculate the sign of this, okay? If there's a quick way to just get the sign of this, that's really all you need. You just need the sign of f of x sub n is m is really all that's needed, okay? So sometimes you can change it so we might be able to figure out the sign, okay? And then pick your two endpoints so that they have different signs, okay? So in this case, f of x on the left is negative, this one's negative, this one's positive, and this one's positive, okay? And so what this means is we're going to get rid of the x on the right, and this will now be my new x on the right. Okay, so keep x of L or x of right, keep the one that has the different sign. Okay, keep the one that has a sign different from the midpoint. And so this will cut this in half. So this is x of m, and so this will be my new x on the right. Okay, and then now I do the same thing. I go halfway in between. I go right there, and I go, okay, what is the sign here? And this one is the thing, and then so we would get rid of this one, and this will become my new x on the left. And then we just keep cutting it in half, and we keep doing that over and over and over again until we've narrowed in onto where it crosses 0. Okay, so you're just, does that make sense? What's going on? And that's all you're doing. You're just chopping it in half, and you're just trying to squeeze it to the point where you can find where it crosses 0. Okay, so these are just numeric methods for root finding. You'll have a little bit of practice on this in your homework, so I'll put that in there. Okay.